we will recreate lithium and sodium. And lithium has how many electrons? 3. So we've got 2 on that first ring, 1 on the second main energy level. Sodium has 2 on the first because it's got a total of 11. And then it's got 1, 2, 3, 4, 5, 6, 7, 8. And it's got 1 out there. So let's get rid of the extra rings. Cut. 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 Okay. Oh, I screwed that up. Pardon? There. Okay. So, we're going down a group here. Lithium sits above sodium, which sits above potassium, which sits above rubidium, which sits above cesium. Atomic radius increases as we go down the group. Can you see why immediately? Okay, so there are multiple reasons why. Let's look at one of them. The first and most obvious is what? More energy levels. Yeah, remember, each energy level kind of takes us a little bit further from the nucleus. It's metaphorical to some degree, but we get further out from the nucleus. There's one other thing, and this was the metaphor I started with yesterday and then said, wrong page, but we're going to go back to it. So here in lithium, we have 3 protons pulling on 3 electrons, and to pull on this outer electron, they have to go through one other layer. They have to go through one shell between them and that outer electron. They can exert a pretty good force on it. That outer electron has got 2 bodyguards in essence. To pull on, let me get rid of my random E that shouldn't be there. So when we look at sodium, we have 11 protons pulling on 11 electrons. Okay. But to exert a force on this outermost electron, it's got to go through 10 other electrons. It's got to go through 2 whole energy levels. Do you think it's a little bit harder to exert a good, strong pull on this electron compared to this electron? Yeah. The nucleus can't pull that outer valence electron in as strongly because there's too much stuff in the way. This is this idea of, you want to get to me? Yeah, I got to go through my 10 brothers. Okay? This electron is fairly well, we call it shielded. It's called electron shielding. So electron shielding. Did I spell shielding right?
No.
I didn't think so. That better? Yeah, that looks right. Okay, so we call it electron shielding, and that's this phenomena that as we get into larger and larger atoms, you've got many more layers of electrons between the nucleus and those outer atoms, those outer electrons, to pull them in. So they're not held as tightly, which means overall, so in addition to the fact that there are just more energy levels on sodium than there are on lithium, in addition to that, you also have this thing that those outer electrons can't be pulled in as tightly, so the whole thing gets, the word I typically use is fluffier. You can think of fluffy atoms, which is absolutely ridiculous. These are not sheep, but it's a metaphor that works. So let's draw potassium. All right, so we've gone one more down the periodic table. We've got potassium. Look at how many electrons are sitting between that nucleus that now has 19 protons and that outermost electron. That's a bunch of electron shielding. So, which of these outer electrons, that final valence electron, do you think would be held the most tightly by the nucleus? Which one's got the best grip on its outer electron? metaphorically speaking. All right, sorry about that. Correction to the number of electrons. Potassium doesn't have anything on the 3D. It hasn't filled 3D yet. It's just got 1 on 4s. Okay, so which one of these do you think would have the tightest grip on its outer electron? Lithium. There's not a whole lot between that outer electron and the nucleus. On potassium, it's a much more tenuous grip. Let me get rid of that last shell that we're not using. It's a much longer distance, and there's a lot more in the way to exert a force on that outer electron. So this thing tends to get fluffier and fluffier and fluffier, bigger and bigger and bigger. As we go down a group, atomic radius increases. Okay? Atomic radius increases as we go down a group. Okay, so as we go down a group, the atomic radius is going to get bigger and bigger and bigger. So, let's try something. I'm going to give you a list of elements. You put them in order of increasing atomic radius, so smallest atomic radius to largest. Okay, so you've got selenium, tellurium, oxygen, sulfur, and polonium. This is group what? Group 16. Put them in increasing order of atomic radius. So, smallest radius to largest. All right, so this one's really easy. Order of radius, we just go straight down the group. Fantastic. Wonderful. So, and it makes sense cognitively. You're adding more electrons. Of course it's going to get bigger, right? Well, let's look at something else. Now, we're going to work with lithium, beryllium, and boron, okay? So now we're looking at trends that go across a period. Now, down a group is easy. It gets bigger, you add more electrons, there's more electron shielding, it gets fluffier and fluffier, la 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 la. Okay, sure, I get that. Let's draw these little Bohr diagrams for lithium, beryllium, and boron. Okay, we've got the Bohr diagrams for lithium, beryllium, and boron. We're adding electrons as we go, right? Beryllium has more electrons than lithium. Boron has more electrons than beryllium. I did something with the sizes of these. Oh dear. So the trend, as we go across a period, is that atomic radii decrease. Well, we've added more electrons. It should get bigger, right? Huh. So we've added more electrons, but what we haven't added, there's something we haven't added. Somebody who has no shoelaces on. What haven't we added? What do you think, Jeremiah?
The brains.
Ah, Sarah, what were you going to say? Yeah, exactly. We haven't added any more energy levels. So while we have here 3 protons pulling on 3 electrons, and there's some shielding to get to that outer electron, here the nucleus is pulling now on 2 electrons in the outer ring. So it's as if you've now got 2 places to pull that outer ring in. And what that means is that you're able to pull it a little bit tighter. Now, of course, this is a metaphor. There are no literal little arrows. There are no literal strings. These are all metaphors. It's a lot more subtle and complicated than that. But they're decent, reasonable metaphors to get your head around the idea. So in boron, that nucleus now has 3 sort of places to pull on that outer ring. And it's able to pull it in a lot more tightly. So, let's practice one more time. Let's put these in order. I'm going to give you a list, and I want you to put it in order of increasing atomic radius. So now we have 5 things that are all out of one period. I want you to put them in order of smallest atomic radius up to the largest atomic radius. Okay, so you've got this. This is pretty easy. You figured out that it's just you go backwards. So your smallest atomic radius in any given period is going to be in group what? 18. Your largest atomic radius in any given period is going to be?
1.
Yeah, group 1. This is easy. Good, 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 good. So let me ask you a question, revisiting that idea that atomic radius increases as we go down a group. Which of these things, and we'll call this we'll call it 1, 2, and 3. So show me voting with your fingers. Which one of these do you think, based on this, would be most reactive? We get back to that idea of loosely held. Remember we said these got fluffier as you went down, partly because this potassium is not able to hold that outer electron as tightly as this lithium does. Well, if you can't hold your outer electron very tightly, you're quite likely to lose it. And that tends to make you more reactive, tends to make you more prone to compound formation and just reactivity in general. Okay, so let's go to our next trend. Do you feel like you have a reasonable grip on atomic radius? Okay, you'll have a FIP tomorrow. Let's go to the next idea. Okay, so it seems like we shift gears, but this is just a side step that we have to make to get to the next rung of the ladder. Ionization energy. We're going to start to talk about ions now. And I think you all know that an ion is?
A negative.
Well, it's just a charged atom. An ion is a charged atom. It can be positive or negative. We're going to start off talking about positively charged ions. Those are cat ions. And if you have a hard time remembering this, the mnemonic that I used for years was, petting cats is a positive experience. And there's my little chem cat. So, petting cats is a positive experience. Cat ions are positive ions. Okay? Now, this is the tricky part. This is the part that always throws people for a loop, and maybe it won't throw any of you for a loop. That would be wonderful. To make a positive ion, do we add or subtract electrons? Okay. We lose electrons. And the thing I used to teach when I taught physical science was that little diagram. So imagine that this is lithium. Right now it's neutral because for every positive there's a negative, so they all balance out. When we lose an electron, now we have a net positive charge. And so this is now a lithium 1+. Okay? So when however many electrons you lose, if you give up 1 electron, you become 1+. If you give up 2 electrons, you become 2+. You get that. I just wanted to make sure we had a good foundation there. So when we talk about making any ion, the process is ionization. Okay? The process of making any ion is ionization. But we're going to talk about IE, which is ionization energy, in terms of positive electrons right now. Okay? When we've got lithium, and it's got 3 protons and 3 electrons, and it's neutral, there is some amount of energy that's required to pull that electron away from the outside. Okay? Because right now it's all nice and balanced, and even though it's not the most stable configuration, which would be the noble gases, it's got an equal number of positives and negatives. It's, sitting at some energy level. To strip this electron away takes some amount of energy. And it's given by this little sort of word equation. The element plus some amount of energy yields a positive ion plus a free electron. Okay? And we call that amount of energy the ionization energy, okay, or IE. Would you guess, because we're talking about this now, that there are periodic trends in IE?
Yes.
You'd be right. Okay, so if we look across a period, there are distinct trends in ionization energy. So let's look at period 2, starting off with lithium. If lithium were to lose that one outer electron, what element would it look like? It would look like helium. Remember when we said everything wants to be a noble gas? Well, if it just lost one electron, it could look like a noble gas. That's not too much to ask, is it? So lithium gives up that one electron pretty easily because that noble gas configuration is very, very, very stable. It takes very little energy to be a noble gas. It's very stable. And so it doesn't take a whole lot of energy to pull that electron off of lithium. It's pretty easy to do. They give up their electrons pretty easily. They have the lowest ionization energy in their period. So if I gave you a list from period 4, or if we went back to that list from period 4, hold on. If we went back to that list from period 4 where we had arranged these in order of smallest atomic radius to largest atomic radius, which one of those would have the lowest ionization energy? Which one? We said in every period, the group 1 element has the lowest ionization energy. Which one here has the lowest ionization energy? Potassium. Lowest IE. Huh. Biggest radius, lowest IE. That goes on potassium's resume. Lowest ionization energy along with the largest radius. Huh, interesting. So here we have bromine, 35 electrons. 7 of them on that outer ring. If bromine lost one electron, would it look like a noble gas?
No.
No. It'd be farther away from looking like a noble gas than it already is. Bromine would much rather add an electron than remove it. So the halogens tend to have the second highest ionization energies in their groups. They don't want to give up an electron. Why would they? They're so close to that stable noble gas formation. There is almost no way that they're going to give up an electron. Now, if we added one electron to this, what would we have? Krypton. Now, this is the thing. This is the stuff. This is it. This is happiness. This is joy. This is stability. This is low energy. It doesn't take a whole lot of energy to be Krypton. It's very easy to be Krypton. Krypton is sitting on a lounger by the pool with a big pitcher of lemonade, just enjoying life with a good book. This is Krypton. Why would Krypton give up anything? Ever. Or take on anything for that matter. Krypton doesn't want to change anything. The noble gases have the highest ionization energy in every period. Okay? So, let's go back to that group we did for period 4 where we looked at atomic radius. Whoops, there it was. So, which one of these would have the highest ionization energy? Huh. Highest IE, smallest atomic radius. Huh. Do you think they're connected? Peculiar. Curiouser and curiouser, as Alice would say. Curiouser and curiouser. So what did we say about why does atomic radius shrink as we go across a period?
There's more electrons.
Okay, more electrons on the outer shell, so
So there's
greater pull. They're pulled in more tightly. Well, if something is being pulled more tightly, it's harder to strip off. Oh! So, if you have a very large atomic radius, what does it mean? It means you're not really holding those outer electrons very tightly. So we said that if you've got a very small radius, you tend to have a very high ionization energy. Why? If you had to describe the relationship between atomic radius and ionization energy, do not yell this out, I want you to write this down on your paper. Would it be an inverse relationship or a direct relationship? So, let's go to a new slide for this. Which would it be? As your atomic radius goes down, as it gets smaller, what happens to your ionization energy? Use your fingers. Point. It goes up. So this is an inverse relationship, and through the magic of little graphical things like this, we can do that. So this is an inverse relationship. When atomic radius increases, the ionization energy goes down. It's easier to strip electrons off a really big, fluffy atom. When you have a very small atomic radius, when you've got something that's tightly holding its outer electrons, it's got a much higher ionization energy. So, now looking at your periodic table, let's look at the F block. Let's look at the F block. What did we say about the lanthanide series? So that's elements 57 through 70. They're all reactive. They're all reactive. These are some pretty darn big elements. They've got lots and lots of, let's see, their outermost electrons are on the 1, 2, 3, 4, 5, 6th main energy level and the 5th main energy level. They've got 4F, 5D, and 6S as their highest levels. That's pretty far out from the nucleus. That's not something that you can hold on to very tightly. So they tend to be very reactive. Now the thing that I want to make clear here is one important difference. Reactive, prone to forming ions, these two things do not equal radioactive. Okay? This is a really important distinction. So these things all have to do with the behavior of valence electrons. This has to do with an unstable nucleus. So, whoops, nuclei. Nucleus. Okay? So this is about an unstable nucleus. It's a proton-neutron thing. Being reactive and or being prone to forming ions is an electron thing. So they are not the same thing, but it's a really common source of confusion because people look at the F block and they go, oh yeah, the actinides are really enormous. That's why they're so reactive and that's why they're so radioactive. Well, yes, but big in different ways. They have large atomic radii because they've got lots of electrons and lots of shielding between the nucleus and the electrons. But they're radioactive because they have enormous nuclei. They got big nuclei. And those big nuclei are unstable. Okay? Okay, so this is a chart on which you probably won't be able to read the names. That's fine. I'm going to draw a few things in for you. There are the elements of the first, whoops. Did that wrong. There are the elements of the first period. There are the elements of the second period, third period, fourth period, fifth period. So, find two trends, and just to make it clear, there is a second fainter line down here. I'll do this. Okay? So, one of those lines is ionization energy. One of them is atomic radius. I don't know if you can make it out on your notes. Probably not. That's okay. One of those lines is atomic radius. One of them is ionization energy. So I want you to find two trends, write them down, and then you're going to compare them in small groups. This is atomic radius. And this is ionization energy. Ionization energy. So most of you noticed right off that, hey, as one goes up, the other goes down, which we talked about. So, woohoo. But did you notice also, so for each period, these two are the first period. So here's hydrogen, here's helium. The highest ionization energy in its period is the noble gas. And then there's a significant drop down to your group 1 element. Now there are a few little, wiggles and waggles in the line. And I'm not enough of a chemist to explain those well. They exist. Variety of factors, I'm sure. But the general trend is up. But if you look at the ionization energy for the noble gas, what happens to it as we go that way? So if we compare, the ionization energy for the group 1 element. If we compare lithium to rubidium, it drops. So that's going down a period. So ionization energy does what as you go down a period? Decreases. Ionization energy decreases as you go down a period. It takes less energy to strip an electron as you go down a period. Let's go back and revisit the other thing we did here. So, as atomic radius increases, ionization energy decreases. What do we know about atomic radius as we go down a group? It increases. So what would we expect to see as we go down a group? We would expect to see a decrease in ionization energy. The bigger that atom gets, the easier it is to strip that outer electron. Okay? So, we're going to stop there. I'm going to show you a quick video that demonstrates that concept really nicely. And I'll give you some time to work on the homework. Okay, so we'll stop this with the... we watched some videos on YouTube. If you search YouTube for alkali metals and alkali earth metals in water, you'll get some great videos. If you missed class and you're watching this at home, you should go look on YouTube for those kinds of concepts. FIP tomorrow.